All right, let's go ahead and get started. Any questions about anything at all before we do? 2.1 is due tonight. Yeah. So you have 2.1 is due tonight. Wait, 2.1?
Yeah, it's on the rubber because it's not. 1.6 is good.
That's what I thought.
It said both of them are good.
Well, yeah, both of them are, but he usually changes it like once we finish the lesson, we'll change it to like.
So what's Canvas say?
Canvas doesn't even bring up 2.1, but like if you go on
Yes.
rubber.
Okay, so yeah, so don't worry about what WebWorks says. I don't really change the due dates in there until after we're done here.
So it's only 1.6.
Yeah, so whatever, get all my due dates for WebWork from Canvas. So just the thing about WebWork, the software is if I want to open things up to you, I have to give it a due date. And then it sorts them all by due date. So I try to put them in order just so I can see them in order. So bottom line for you all is don't worry about the deadline for a thing until it shows up in Canvas. So tonight 1.6 is due. 2.1 won't be due any earlier than Friday. I put quiz number 2 up as well today, like in the last half hour or so. All right, so also I have graded quizzes for you. If you gave me a paper copy, hang out and I'll get it back to you today after class. All right. So talk about how to find derivatives. And really, you know, by definition, what a derivative is this rate of change calculation, which, you know, not a coincidence, looks a lot like the way you would calculate a slope. And we can use that to find derivatives at basically we can find the slope of a tangent line or the slope of a curve at a single value of x. So let's go ahead and remind ourselves what the definition of derivative is. So let me back up. I want to find f prime of 1. So basically, I want to find what the derivative of this function is at the location where x equals 1. So that's the limit as h approaches 0 of this thing here, f of 1 plus h minus f of 1 all over h. So now that I have kind of this framework here, I can start, you know, taking advantage of my function notation and filling a lot of these building blocks in. Based on what my function is up here, what is f of 1 plus h going to look like? How can I express that?
2 over 1 minus 4 plus 8.
Yep, 2 over 1 minus h.
Would be minus 4.
Yep, 2 over 1 plus h minus 4 minus f of 1, which is just going to be, write it long form for now, 2 over 1 minus 4 all over h.
It's like x plus h is literally wherever the x value is in the function plus h.
Yeah, so basically, and let's think about, you know, what I'm about to graph for you is not this function. It's just something generic, but usually a is the point, or I mean, when I define this for you the first time, a is the x value where I wanted to find this derivative. In order to calculate a slope, though, you need some separation between those x values, which we call h. So if I have a curve here, where are you, cursor? So if I have a curve here, basically I'm going to try to find the slope between those 2 points, but I'm going to keep a stationary. I'm going to keep it fixed, and I'm going to dial h lower and lower, trying to make those 2 points as close as I can to each other. So in this case, our first a is going to be 1. I can't really find that slope without dealing with this limit. It's usually called a difference quotient. I can't really find derivative without kind of letting h approach 0. So yes, I'm really interested in the derivative at x equals 1, but in order to think about that, in order to work my way up to that, I have to get some distance of separation away from one. So that's what the H is really doing. From here, really what we're doing is simplifying. So the limit as H approaches 0 of, so do we notice anything that's going to happen that's convenient for us? Or is it still going to look pretty ugly? The 4s are going to cancel, so I just should have 2 over 1 plus H minus 2 all over H. Can I evaluate the limit yet? Nope. What should I do to, I mean, I'll tell you right now, the limit exists, so we just have to keep working up to it algebraically. So what's something else I can do here to continue simplifying?
Get the H out of the denominator.
How do we get the H out of the denominator?
Multiply by conjugate.
Multiplying by conjugate will work, but there's something a little more direct that might help us. So just to kind of, since the conjugate was brought up, conjugate's really, really nice for like annihilating square roots. I mean, I think that's probably the biggest thing we used it for, right?
Mhm.
We don't really have that situation here. What is the problem right now? Go ahead.
It's 2 over the 1 plus H minus 2, so you can times the minus 2 by, wait, can you? Maybe you can. No, it's not a rational function. I was gonna say you could times it by the.
I mean, here's the thing, it is a rational function. It's just hard to see right now.
Oh, yeah, because it's negative 2 over 1.
So-
you can times it by the 1 plus H, so then you could.
There you go. And that kind of hits at the question I was about to ask, which is, what is the problem here? And the problem here is that you have this compound fraction within a fraction. So in order to do that, let's try to clear out that extra denominator. So we're going to multiply this expression by 1 plus H over 1 plus H. The limit as H approaches 0 of 2 minus 2 times 1 plus H all over H times 1 plus H. So maybe it's not obvious yet, but we're kind of working up to a rational function that we can deal with. From here, do I get anything that conveniently cancels? Yeah, I'm going to get 2 minus 2H, right? So all said and done, negative 2H over H times 1 plus H, which I can do this. Can I evaluate that limit now? Yes, you can. What does this limit equal to? Negative 2, right? So all that to say that if I were to graph this, the slope of this function where x equals 1 is negative 2. I am not going to, I'm going to leave this other one as a practice thing for you if you want to go do it. But any questions so far about how we did the f prime and 1?
Yeah, that 1 plus, it's just not that 1 plus H, and that just went away because like you can cancel it out when you want.
Yeah, basically what's going on is, yeah, so, and we purposefully chose 1 plus H because multiplying by that's going to cancel out the fact that at some point I'm dividing by 1 plus H. So that's why I just have the 2. The first term in the numerator is 2. Second term becomes negative 2 times that binomial that I multiplied through. So, and where's my cursor? This derivative here is going to be negative 2 over 9. So I'm leaving this here for you as basically you can do exactly what we did here and wind up with the same answer. And just if you want to go back and practice, that's the finish line for this one.
So you would just do the same exact process.
Yeah, pretty much. And really, this two important things are going on here. Basically, a procedure and a concept. Number one, the concept. Do we understand why this, this unfamiliar thing why this is a derivative, like where it came from. If not, now's the time to ask me any clarifying questions. Go ahead.
Don't understand where it came from.
Okay. We could probably answer that. I'll give you a short answer and a long answer. The short answer can probably just be one word. Where does that calculation come from? Slope, right? I mean, at its heart, that is what that is doing. I am taking a change in y values. So I have f of 1 and f of some other point 1 plus h. Two different y values and take their difference. And I'm also taking a difference in x values, which is probably a little harder to see. My two x values are a and a plus h. What's a plus h minus a? It just comes up to h.
So h is the distance between the two points.
Yeah, it's the horizontal distance between the two.
And f1 and 1 plus h is the distance between the vertical distance.
Yes, so this is literally, you know, what's the catchphrase, rise over run? Difference in y values is rise, difference in x values is run.
Okay.
So, I mean, the short answer is that's a slope calculation. The thing that makes it a derivative and not just your standard slope calculation is the fact that we're taking this limit. Instead of letting these 2 points, these two x values exist apart from each other, now I'm trying to see what happens as I move one onto the other. So this slope right here that I got of -2, that is not a guess of like some neighborhood around x equals 1. That is the slope at that 1 point. So that's the concept. Procedurally, it's basically, you know, probably have to brush off some algebra skills you haven't used in a while, or maybe some ones you haven't ever used. Basically, you're just trying to get this thing from here, where I cannot evaluate this limit, potentially into something like this, where the limit is defined.
Yeah, that's what I was saying. I was getting confused on, because I was assuming we're actually solving for h.
Yeah.
But,
No,
yeah.
so, everyone, that's another thing to bring up. It's not solving for h. What is h's job here?
To rotate you.
Okay, the only job that h has is for us to make it really small. And to see what, and so basically h is the thing we're controlling. We want to make h very small, and then we want to see what the slope does in response to it, to h getting small.
Okay.
Go ahead.
So then in essence, we should be trying to get to some constant over 1 plus h, because that way it'll become anything over 1.
Yeah, essentially, and you're kind of seeing the common thread here is where basically, and it's not luck, and this happens for any time the derivative exists, this h will get canceled. And like in this, I remember when I was kind of first learning this, it seems like, all right, you're just picking these things that work where that h will get canceled. Really, it's inevitable. It's inevitable when the function's derivative exists. Anything else about this one here? All right. So this is the question I asked you on the very first day. Can we find the speed? Now, hopefully you agree that we can do this. So we can actually find this exact speed. So really what I'm asking for is, I'm giving you s of t. I am trying to find this thing, s prime of 5. So s stands for the distance that it falls in meters. I'm trying to find speed. Another way to say speed is the rate of change of distance over time. So basically, I'm trying to, what I asked you on the very first day is I want the derivative of this function where t equals 5. So based on the definition we've been working from, how can I set up this derivative? S prime of 5.
So 4.9, and then in parentheses, 5 plus h squared.
So 4.9 times 5 plus h squared minus 4.9 times 5 squared all over h. Missing a very important thing that I left space here. Yeah, so remember, without that limit, this is just a slope, right? You really need that. I want to know what happens when h is getting very small. So if we can find a number out of this, then we're going to stop guessing at what that speed is. We're actually just going to find it. So from here, Let's not expand anything until we're sure it's gonna help. So 4.9 times 25 plus 10h plus h squared minus 4.9 times 5 squared. Oh, sorry, missed something really important. All over h, right? Are we okay with the fact that this 4.9 times 25 is going to cancel this 4.9 times 25? Okay. So if we're okay with that, then I can rewrite this like this. The limit as h approaches 0 of 4.9 times 10h, which is 49h, plus 4.9 times h squared. The two constants cancel out, and I have this. So this is the situation I wanted, right? One more rewrite, and we can get to a place where this can be evaluated. The limit as h approaches 0 of 49 plus 4.9h. What is that limit? 49. So if we go back a few slides, I think we estimated the speed was like just a little bit above 49, something very close, right? So we can get as close as you want to this value, which is the speed of 49 meters per second, but now we actually have a way to guarantee this. No error inherent in that. Any questions?
1 second.
Yeah, of course. Any questions about what we did there, or how we got that speed, why we can trust it absolutely?
So that's the speed, like exactly.
Yeah, at 5 seconds. If I wanted to know at any other time, I'd have to redo this calculation. But yeah, at 5 seconds, that is the speed.
And that on the bottom one, that's 4.9, not 49, right?
The left-hand term is 49.
49.
The right-hand term is 4.9h.
Okay.
The 4.9h gets annihilated when I evaluate the limit. Yeah, right. All right. Let's go ahead and keep going. So based on that, okay, well, based on that, I want to find the speed after it has fallen 450 meters. So based on the information given, what do I have to do? What's that?
Same thing, just in reverse. Yeah, set it equal to something.
Set what equal to what?
We have to set
Right, so here's derivatives are powerful, but I have a function here that's distance in terms of time. In order for me to use that to find the speed, I need to come up with a time. So in this case, I need to find when that time is. When will it have fallen 450 feet? So t squared equals 450 over 4.9. The square root is about 9.58. So I have a time value of 9.58 seconds. Should I expect the speed to be smaller or greater than it was before? Should be greater, right? Gravity should make it go faster. But we can set up the same kind of calculation. So I want S prime of 9.58. Set up the same limit, so 4.9 times 9.58 plus h squared minus 4.9 times 9.58 squared all over H. Is this looking familiar to what we just did though? So what do we expect to happen if we were to expand out that numerator? Yeah, so the constants are going to cancel again, right? So I'm going to have 4.9 times 2 times 9.58H. What is 2 times that? $19.16. Left off something very important. So again, I should be in a place where I can just cancel out an H. So this limit is going to be, let's just say 93.9 meters per second. Go ahead.
The second one, why is it 4.9 times 19.6?
Yeah, I abbreviated some things that maybe I shouldn't have. So let me put that up in the margins. Going from this this squaring here, this is going to come out to be 4.9 times 9.58 squared plus 2 times 9.58 times H plus H squared. So basically that's just me kind of, if I were to FOIL out that binomial. And basically the shortcut I took was I know that that constant 4.9 times 9.58 squared is going to cancel out the far right term. So all I'm left with is going to be 4.9 times 2 times 9.58. I think, did I do it wrong? No, I don't think so. I think okay. Was that what you were after?
Yeah.
Okay. Yeah, I think I just skipped a step. Any questions about how we calculated the speed in either case? Does it seem kind of tedious that we have to go through this for every single timestamp we want? Okay, so let's try to get away from that. So I want to find the derivative of this thing here when x equals not a number, but let's just call it a for now. So some dummy value a. So I want to find the derivative of this thing. So we'll call it f prime of a. And how do I find that? So all derivatives pretty much are going to start from here. I mean, they all do by definition. So the limit as h approaches 0 of f of a plus h minus f of a all over h. What is f of a plus h in my case?
Would it be the square root of 1 minus 3x plus h?
1 minus 3. You said x. I'm going to change that to a. But yeah, I mean, why am I using a instead of a number? What's that?
Your number is a.
Right, but why don't I just use a number? Like what value am I adding here that we didn't have before? When I say value, I mean, why is this better? I can calculate it for any value, right? So yeah, I'm just going for versatility here. So there's f of x, f of a plus h. Subtract off 1 minus 3a all over h.
The first one's supposed to be 1 plus 3.
It's not supposed to be. Thank you. All right, so from here, obviously can't evaluate that limit directly. So what can I do to help me get there? This time the conjugate's going to be valuable because, and I think this is just a good question to ask whenever you're stuck with the algebra, is ask yourself, like, what's the problem? What's the obstacle? In this case, the obstacle is that can't really subtract those things because order of operations says the square root takes precedence. So I'm going to multiply this fraction by what?
1 minus 3 times a plus h plus.
Right. So 1 minus 3 times a plus h minus 1 minus radical 1 minus 3a all over h. And we're going to multiply this thing by the conjugate, which is same terms, opposite sign. All right, pretty nasty looking. So what did that do for us? Anything? Square roots are gone where? On the top, right? So hopefully that helps. So I know basically because of, the reason I use the conjugate is because I know those when I FOIL those things out, I'm going to lose the middle terms. So first term squared is just going to be 1 minus 3 times a plus h minus 1 minus 3a all over h times the conjugate we brought in.
When you put the square roots back in the denominator, does that like not fix anything? You still have square roots in your problem.
Well, they're in the denominator now. So hopefully it doesn't matter. Otherwise, what we just did didn't help. So yeah, you're right. There's really nothing you can do to get rid of the square roots. But maybe they're not a problem when they're in the denominator. From here, where can I go? Can I evaluate the limit? Not yet. I'm still going to have h equals, setting h equal to 0 is going to make the whole denominator 0. And really, keep in mind that our goal has pretty much always been to wipe out that h in the denominator. Do we see a way to do that yet? So let's rewind a little bit. What did we say was the problem? Why did we use the conjugate to begin with?
Get rid of the square root on the numerator.
Got rid of the square roots from the numerator. So let's keep taking advantage of the fact that they're gone. I can, if I expand all that stuff out, hopefully something's gonna work out for me. So the limit as h approaches 0 of 1 minus 3a minus 3h minus 1 plus 3a all over the square, or h times the square root of 1 minus 3 times a plus h plus radical 1 minus 3a. So 3a minus 3a, 1 negative 1. Do we think it helped?
Yes.
Absolutely. So this h cancels this one, and now can I evaluate the limit?
Yes.
What do I wind up with? Clearly negative 3 something, right? Negative 3 over. So let's talk about what's going to happen here. As h goes to 0, what's going to happen with this thing here?
Just.
It's just, yeah, radical 1 minus 3a. So it's the same as the other one, right? So because of that, It's just this 2 times the radical of 1 minus 3a. So any question about how we got there? Obviously, the algebra gets a little hairy.
The H in the denominator at the end of the calculus.
Where did it go? Why is the h in the denominator no longer there?
Is cancel because it's negative 3h.
Oh, I'm sorry. Solomon, which h you're referring to? The one I crossed out or?
No, the one inside. Yeah.
Okay. Yeah, where'd that h go?
I determined that there's 0.
Right, so once I cancel out the h that's being multiplied by that other expression, I can now evaluate that limit just through substitution. So yeah, didn't go anywhere. I just evaluated the limit, and since I'm adding h instead of multiplying it, everything's okay. Anything else about this thing?
So that's the derivative.
That is the derivative, and I will make it clear, f prime of a. So this is, and this thing will be true here for any a that actually, where this is actually defined. Right.
And once you find the derivative, you still have to put the limit equals h to 0 now that h is gone.
Now, I mean, here's the thing. So if we go back an example or two, we were finding the derivatives of one function at one place, right? Now that we've gone through all this, we are now able to find, so this derivative right here is a lot more powerful, but it's still only good for that function. But if I ask you what f prime of 2 was, by no means should you go through this again.
Yeah,
You have this. You came up with a formula. No one really works for that exact function, but still a formula that allows you to find the derivative at whatever point you want.
So for like any value of that function, that equation will work.
Yeah, that's the derivative. So that is the derivative of this function. And one thing that we're going to get to just a bit is this a function unto itself?
Yeah.
If I plug in a value for a,
Yeah.
will I get a value for f? Yeah. And only one, right? So the derivative is a function unto itself. Those two, I have two functions here. One's called f, one's called f prime. They're related to each other in a very specific way, but they are both functions. Anything else? Okay. Yeah, let's go ahead and do this one. I want to find the equation of the tangent line to this function. So let's rewind a little bit. What is a tangent line?
It only hits 1 point.
It only hits 1 point, right? So if I were to, I'm not going to draw this exact graph, but if I were to graph this thing, what would it look like? Based on the way the equation looks.
It'd be a U facing downwards.
Facing upwards. What do we call this U thing?
Oh,
It's parabola, right? So, and I'm looking for a tangent line, right? So what is the line going to have in common with the curve at the point where they touch?
Same slope.
Same slope, right? So basically the first thing I'm asking you for is, I want to find the slope of this function. And let's kind of do what we just did. Really, I only want the slope of that function at 1 point, but while we're at it, why don't we just find the slope at whatever point I want? So f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. Please stop me if you need to, otherwise I'm gonna run through a couple of steps. It's kind of on my own here. So this will be a plus h squared plus 3 times a plus h plus 5 minus a squared plus 3a plus 5 And I'll expand all this stuff out. So a squared plus 2ah plus h squared plus 3a plus 3h plus 5 minus a squared minus 3a minus 5 all over h. It's a lot of nastiness. Did anything work out for me there? There's a man, and this is not a coincidence. So now I have 2ah plus h squared plus 3h all over h. So now I can rewrite this thing like this. The limit 2a plus h plus 3. Can I evaluate that? Yeah, that's just 2a plus 3, right? So I have this derivative, f prime of a. Basically, I have a formula now for the derivative of that function. I want to find the equation of the tangent line. What information about the tangent line can I get from the derivative? Slope, right? And that's really what a derivative is. It gives me instantaneous rate of change or slope of a tangent line. So I want f prime of what value? 2. That's the x value I care about. So f prime of 2 is going to be 2 times 2 plus 3, which is equal to 7. How do I find the rest of this equation?
Now you have all the things you need.
I almost have all the things I need. I mean, yeah, I have all the things I need to solve for b. So y is equal to 15, m is equal to 7, x is equal to 2, which means b is equal to 1. So my final equation is this. Y equals, what does his slope was? 7? 7x plus 1.
So that's the significance of, like, when they give you the y value point, that's, you need that solver here.
Yeah, if I did not give you the y value, I would be able to do this.
No.
I heard one vote for no, and I saw someone else nod their head. I actually don't need to give you that y value, right?
You can substitute.
You can find
Yeah.
it. So you need a y value. You just have the means to get it. Anything else about this one here?
So that y equals m supposed to be is only for the tangent line, right?
It is only for the tangent line, yeah, so this is a pretty good representation here, even though parabola doesn't look exactly like this. Parabola obviously has no straight line components anywhere, right? So let's say that line is this line here. What are the only two things that line has in common with that parabola?
And 1 point.
That 1 point, so they share one location. And what at that location, what else do they share?
Same slope.
The same slope. So this right here only really represents that curve at that one place. Any other questions about this? Go ahead.
And then technically you could go back to the original thing and just solve for that 1 point and not solve for every point. You could do the same.
What do you mean by that? What am I looking for?
Because you're looking for the value at 2, so couldn't you take the original thing we were doing where we don't use the a?
Oh, yeah.
Yeah,
We could have entered common too. I'm just showing the value that has.
Yeah.
If I wanted to switch this up on you and say,
that you find multiple points.
yeah, I could find the tangent line at 1,8. Now that would be very quick now because I don't need to go find the derivative again. I mean, other than using the formula we got for it, the 2a plus 3. Doing good? All right. All right, from this graph, I want to find f prime of 3. Not gonna be able to find it exactly, just kind of based on the information that I have made available to you, what could we say about f prime of 3? Positive, negative, or 0? Okay, why is it positive? So you have a function, and the key word is the function is increasing at that place, right? Graphically speaking, what tells you the function is increasing? Going upward, right? So we okay with the idea that the f prime of 3 is a positive number? We think it's greater or less than 1, about 1? So steeper than, bigger than 1? Let's call it 2. Again, I mean, based on where I got this, there's no way for us to know exactly, but if you tell me a negative number, I can pretty much tell you you're wrong. But positive number, and I think saying it's bigger than 1 is also pretty easy to justify. How about if I ask you where the derivative was equal to 0? So if I say f prime is equal to 0, obviously that's not true everywhere. So where are some x values where that might be true?
4, 1.
Okay, you said 4. Why 4?
The function, it goes from an increasing to a decreasing interval in the same
Okay.
figure. And the
So-
opposite, I want.
So, and that's really well said. When x equals 4, as I kind of approach this going from left to right, increasing, decreasing. So if you went from increasing to decreasing, what? So another way to say this, the function goes from increasing to decreasing, right? What does that mean about the derivative over here?
It has to equal 0 at some point.
Right.
Yeah.
Well, I mean,
Because it's going from up to down.
Yeah.
right. So the function is going from increasing to decreasing, which means the derivative is going from positive to negative, which means somewhere in between.
The slope has to be.
Since it's continuous, it has to cross through 0.
They also equal 0 at x equals 1.
Yep. X equals 1, x equals 4. Anywhere else where you can make this claim. Not that I've shown you. So yeah, anytime you're, and we'll put some more vocabulary and specifics behind this as we get deeper into this, but you're already hitting on the key ideas of going from either increase to decrease or decrease to increase.
The f prime of 3 is approximately to y again, because that's almost what the slope is at that point.
Yeah, right. So are you okay with why I said it can't be negative?
Yes.
Okay. And why I said it's probably bigger than 1.
Yeah.
Right. And that's really what we're doing there. I mean, when we're looking at a graph, I mean, a derivative, we're going to talk about it in a lot of different ways. But when you're looking at a graph, probably the easiest way to think about rate of change is just by looking at what the function's doing, looking at what you imagine the slope to be.
Would we ever get a question like that, like estimated value?
Absolutely. It's a
But then-
totally fine, fair question.
But then couldn't you like literally say any positive value?
If you told me 1,000, I probably would argue with you.
So within reason.
Yeah.
Okay.
I mean, I can't hold you down to one answer if I ask you something like that. But if you give me 0, I'm gonna have an argument. But yeah, that's totally fair. I mean, and really, if I ask you something like that, I'm really just trying to see, do you even understand what a derivative is? Just give me something reasonable. Good question though. Anything else on this? All right, one idea we haven't talked about yet is, I mean, everything we've looked at, the derivative has existed, right? So that, another way to say about that, let's say about those functions is, those functions have all been differentiable. So differentiability means this. A function is differentiable at A if the derivative exists at A. And those two things are, it's called an if, like an if and only if relationship. If one's true, the other must be true in both directions. If f prime of A exists, the function is differentiable at A. So what does that mean? Why would that derivative not exist?
If it's either undefined or inconsistent, like not continuous at the same point.
Say, when you say it doesn't exist, what do you mean by it? What's
The value of A, like in the function, like where you're finding Or you're finding the derivative doesn't exist.
Okay, so f of a does not exist.
Yeah.
Is there another way we could state that?
If the y exists.
I mean, yeah, why? So, I mean, y can exist and the derivative not. But what I'm saying is this. So we're saying that f of a does not exist. Basically what I'm saying is, or another way to say that is f is not continuous at x equals a. And that's one thing we'll get into more details and I'll explain more on a later date, but if a function is not continuous, it cannot be differentiable. So that's one way this can fail to exist. Did you have something?
Oh, I was gonna say there's gonna relate back to what you said earlier, like on itself,
Right,
because it's continuous.
right, right. So, and that's great. Keeping in mind that a derivative is a function unto itself, keep in mind what that means for a function not to be well defined. One other thing I want to point out to you is this. Remember, a derivative, we're going to talk about derivatives a lot of ways in here, but really at their heart, derivatives are all come from this thing. The limit as h approaches 0 of f of a plus h minus f of a all over h. And this is equal to f prime of a. So all that to say that derivative is this, it's not really a brand new thing. It's a limit. It's this specific kind of limit. So all the ways that we've seen that a limit might not exist, that applies to this. Think about so one of the ways that limits have failed to exist that we talked about. Or I guess we talked about a few different kinds. Oh, go ahead.
Left and right.
Yeah, the left and right might not exist, or might not exist. They might exist, but they might disagree. So I think we call that a jump discontinuity. What other kinds of continuity? Or go ahead.
If it oscillates.
If it oscillates, I mean that's kind of the same thing. It just doesn't converge to a single number. So we've seen that before. What else? Go ahead. Yeah, when it goes infinite. So all those kinds of discontinuities that can exist in the generic functions we've talked about. Remember, derivatives are just their functions unto themselves. So basically all of those same dangers apply. So when we're asked about whether a function is differentiable, we're really saying, does this limit exist? Or does the derivative exist at a certain place? And everything we've done so far, the derivative has existed because kind of cooking it up that way, but we will come to examples soon where the derivative just fails to exist. So it's good to recognize that that can be the case and to not just take it for granted that the derivative of a function exists. I think I can give you an example if we go back just to the last slide. We came up with a derivative for a square root function that maybe it's helpful to talk about when that would actually exist. For what values of a would this derivative exist? Maybe a better way to ask is, what would cause that derivative not to exist? If a equals 0? I think a equals 0 is probably okay. So when you say 0, what are you really looking at? You have something? If what's positive? If a is positive, I actually think a being positive could be a problem.
Anything less than 1/3 not exist.
Anything less than 1/3.
Or
I think it's greater than 1/3, right?
Yeah. Greater.
So how'd you get there? How'd you get to that 1/3?
You have to set the denominator to 0 and then you put anything
Right.
greater than 1/3.
So a couple things I'm after, right? I need this denominator not to be 0. What's the other problem I run into though?
You can't go negative. You can't have the inside the square root be negative.
I also need 1 minus 3a to be positive. So I'm not gonna figure out what the whole domain is, I just wanted to highlight the fact that we have a function, and functions, whether or not we say what they are, functions have domains. This one has a domain where, I mean, you kind of got to the end of the inequality. I need a to be bigger than a third for this derivative to exist. And if you look back at the original function, that's almost totally true for this function. For the function, for the original function, I can have x equal a third, right? But for the derivative, I cannot have x equal a third. So other than that, the domains are the same. Any questions on any of that before I wrap up? All right, let's go ahead and stop there. I have quizzes for people who turned in a hard copy. Otherwise, I'll see you Friday. Oh, I'll just remind you I have office hours tomorrow for the first time in the MCC down the hall. I'll be in there from 2 to 3:30.
What, is that like, there's a room posted on campus?
It's on my syllabus, yeah. It's room 303. Scared? There you go.
Yeah.
How you pronounce it?
Just video.
I meant to ask you that.
Honestly, it's not make sense, but you got some great.
Yeah, I think I would have not done that. I did give us these, right?
I think so.
Yeah, I did. No, tomorrow from 2 to 3:30, and then Friday from,
Friday.
I think it's 12 to 1:30.
Okay.
It might be 12:30 too. I haven't memorized it yet, but it's on my syllabus.
Okay, thank you.
Good.
So let's just like. Let's see. Figuring out how to put all that.
Yeah.
I got to where maybe 6 or 3. Because each is 0.
Right.
Yeah.
So, yeah, so. So you're trying to get into y equals n equals b form. You got -9, that's correct for the derivative.
Yes.
What does this tell you about this line? It's not the y equals -9. Think about what a derivative tells you about a function. Tells the slope, right? So that is your m.
-9 y 1 plus b.
Yeah, and you should, so they give you an x value?
Yeah.
Oh, yeah,
Yeah. So then it's just 3. Okay.
Yeah.
That makes sense. All right, thank you.
that's fine.
Right here, okay. So this is one of the problems. It's a really hard one to live with the square root there, and you said conjugates are really gonna get square roots, but like, how do you do a conjugate right there?
So conjugate in that case is not gonna help because if you have a square root plus a square root,
Yeah.
in that case, you just have they're all collected on the same square root. So what is it, radical 3 plus 6x?
Yeah, it's x squared
Over,
over 5 plus 3x.
okay. So something we did here that we did an example like this where
This one was tricky.
not the greatest way to think about it, but what's the highest power of x in the denominator?
1.
How about in the numerator?
It's 2, but it's in the square root.
So it's 1, right? So you might have some suspicions based on that
It's just 2.
So it's
but you know, you can think of it as 1 if you're taking the square root of everything here. So something I
I
might
said 2, I meant to limit, sorry.
Yeah. I don't think it's quite 2. So something I might encourage you to do is this. You can think about the highest power of x being 1 and do this manipulation to it. But if you want to have a way to deal with the square root, you can think of 1/x as the square root of 1/x squared. Now, because of that, I can just bring these together, right? So this will equal the square root of 1/x squared times 3 plus 6x squared. And then from there, you have a much better chance of being able to evaluate what that limit is.
Okay. So that 1/x right there is how you, like, if there's a if it's like a square root,